Okay, so we'll begin with the post-lunch but post-afternoon session. Next talk is by Akash Kumar, who will tell us about planar partition oracles.
Thank you very much, Eric. So thanks everybody for sticking around. So today I'll be telling you about planar partition oracles for bounded degree graphs, and I'll show you how you can implement it in poly 1 over epsilon time. This was joint work with Seshadri and Andrew Stolman, and the reason I say was is because it's kind of old now. This appeared in Fox 21. Yeah, so apologies about that. Pretty old work. Okay, so let's get familiar with the setup. So let me begin by reminding you what planar graphs are. So these are graphs that you can draw on a two-dimensional plane without its edges hitting each other. So this is the complete graph on 4 vertices. It's a planar graph. It's just that I've drawn it badly. You can fix it like so. All right. So the graphs in this talk, all of them will be bounded degree. All right. So after a while, I will stop emphasizing that these graphs are bounded degree graphs, but every single graph in this talk will be bounded degree. All right. Okay. So what do we know about planar graphs? So we know quite a bit, and like this is a very cool theorem by Lipton and Tarjan, the so-called balanced separator theorem. The idea is something like this. You got a planar graph, does not have to be bounded degree. What you can do for me is you can identify this tiny little subset of merely root n vertices, such that if these vertices are deleted, then your graph breaks up into a union of connected components. You can assemble some of them on the left, the remaining ones on the right, such that the total components that go on the left and right, they have roughly the same size. The size is between n over 3 and 2n over 3. All right? And this facilitates lots of divide and conquer algorithms on planar graphs. Right? A lot of algorithmic progress on planar graphs use this as a stepping stone. All right. So if you were to recurse the applications of planar separator theorem, you recursively keep applying this separator theorem to the pieces that are produced, then what you can show is that by recursive application, you can afford to delete some mere epsilon fraction of the edges, right? Such that all the connected components that remain, their size is merely 1 over epsilon square. Right? This is pretty impressive because imagine taking this process to the extreme. So you produce singletons, singleton vertices, all the edges go between these components now, right? And what I'm saying is that, you can afford to fatten up your pieces a teeny tiny bit. You can afford to have their size be 1 epsilon square, and you will lose very few edges that run between these pieces. These decompositions have a name. They go by the name hyperfinite decompositions, and they are obtained by recursively using the planar separator theorem. So they were already used in several prior works. The most notable one, or the earliest one that I know of, is the work by Alon, Seymour, and Thomas from '94. And the reason hyperfinite decomposition should be interesting to this crowd is because, if I give you hyperfinite decomposition, a pre-processed hyperfinite decomposition, you can now do the following tasks. You can estimate a whole bunch of interesting graph parameters fairly quickly in constant time. So here is how you would do it, for instance. So let's think about the max cut problem, the max independent set problem. You want to approximate the size of the max independent set. So what you do is that you pick a random vertex. It falls inside one of these hyperfinite pieces. You go and in time exponential in size of this piece, in time exponential perhaps in 1 over epsilon square, you find the max independent set inside that piece. You pick a few random such sample pieces, you estimate the max independent set in all of them, and you just scale back to get the final answer. Right? And this trick can be used for a wide variety of graph parameters. In time 2 to the 1 epsilon square, you can estimate the max independent set size, the max cut size, a whole bunch of other things can be estimated. Right? So hyperfinite decompositions are interesting. And just to make sure that the point goes across, I would like to reiterate that we are going to be talking about bounded degree planar graphs. Actually, more generally speaking, it's bounded degree minor free graphs for a minor of a fixed size, but you can ignore that comment. So bounded degree planar graphs are epsilon k hyperfinite with the parameter k being 1 epsilon square. And what this means is that you can break the vertex set of your graph into fairly tiny connected components of size merely 1 over epsilon square by deleting only an epsilon fraction of the edges. Any questions so far?
When you say epsilon k hyperfinite, you mean k is the size of the connected?
K is the size of the connected component. All right. Great. So let's keep going. So what I'd like to do is first I'd like to show you the prototypical bounded degree planar graph, and I'd like to show how you can identify these subsets of size 1 epsilon square inside this prototypical planar graph. So the prototypical bounded degree planar graph should be the root n by root n grid. So whatever algorithmic results you can produce for this instance, they kind of extend to all bounded degree planar graphs. Like that's just a throwaway comment. We'll come to that later. So let's see how we will break the vertex set of this graph by deleting merely an epsilon fraction of edges into connected subsets of size 1 epsilon square. The idea is to just pull out the tiles. So you pull the tiles out first in the vertical direction, then in the horizontal direction. And these are the green tiles, 1 over epsilon by 1 over epsilon that you will produce. And you can verify that the number of cross edges is merely an epsilon fraction. Okay. All right. So what's our goal? So my goal is to assume that you have access to the adjacency list query model of your graph. And what I'd like to do is I'd like to build for you an oracle that returns to you the hyperfinite piece containing the vertex v in time merely polynomial in 1 over epsilon. Right? So I want to find the hyperfinite piece containing the vertex v fast, but there is an annoyance. There is an annoyance. The annoyance is this, that there can be multiple hyperfinite decompositions that your graph might admit. Right? So for instance, this is another hyperfinite decomposition, which is different from the hyperfinite decomposition I showed you earlier. Now the annoyance is something like this, that look, you got a vertex v, and you're supposed to tell me the hyperfinite component containing the vertex v, and I have not told you which hyperfinite decomposition you should use. Should you use this one, or should you use the one on the former slide? All right, so we want to address this annoyance. The way it's typically addressed is by allowing you some kind of very mild preprocessing. So the kind of preprocessing you are allowed is you are given access to this read-only random tape. Now, sorry for this bad drawing, but now you're going to be stuck with those drawings. So the idea is that you have got access to this read-only random tape. It's going to be initialized with some random bits, and you should think of trying to come up with a randomized algorithm that's going to give me access to some hyperfinite decomposition. The idea is something like this, that once this randomness is initialized, your algorithm becomes deterministic, and it deterministically is now thinking about one specific hyperfinite decomposition. Right? There is one specific hyperfinite decomposition that gets fixed as a function of the randomness that was used earlier. So let me make the goal more clear, because I'm aware that at this step, the goal might not be entirely clear. So again, what I want you to do is I want you to build an oracle access for me to some hyperfinite decomposition. And the way I'll state this goal is that you want to build this primitive that runs in time polynomial in 1 over epsilon. And for a vertex which should return p of v, where the size of p of v should not be too large. It should be merely some polynomial in 1 over epsilon. The graph induced on p of v should be connected. And there is some randomness entering the picture. This randomness should appear somewhere. Where does it appear? It appears in the last condition. I want you to return a legitimate hyperfinite decomposition with good probability at least 2/3. I want to make sure that the probability that the number of edges that I'm cutting is smaller than epsilon fraction is large. Right? The other two items, I want them to hold with probability 1. Is the goal clear?
If you and v are in the same p of v, then
Consistency.
have consistency.
I should have consistency. So yeah, I mean, that I did not emphasize, but you are absolutely correct. Ronit can correct me that you call this query order obliviousness, right?
So this is the same as LCA?
Yeah, this is the same as LCA. It's just that the random string that you are allowed is fairly long. Yeah. Okay, was there a question? Okay, so let's move on. So you might be wondering that, hey, why should I care about this goal, right? I mean, sure, that's a nice little question you can concoct, but why care about this in the first place? So the reason is because, there are some interesting applications to think about. So I believe Christoph is not here. So Hasidim, Keller, Nguyen, and Christoph in 2010, they described that, if you could implement this primitive for me, you would be able to get two-sided testers for planarity with the same query time, right? The query complexity would be the same as the query complexity for setting up this partition oracle, so to speak. All right, and then Levy and Ron refined their analysis to give more efficient partition oracles. Also, as we discussed already, once you have this routine handy, you can use it to estimate a whole bunch of graph parameters. Okay, and then like in joint work with Sabyasachi and Sheshadri, and also in a previous work, Newman and Sohler, notice that you can use this primitive to obtain an exponential in 1 over epsilon square query complexity testers for all planar properties. So what I mean is something like this. Think about planar and triangle free, planar and Hamiltonian, planar and what have you, planar and perhaps an undecidable graph property, right? No matter what graph property you are given, you get a tester for it with query complexity merely exponential in 1 over epsilon square, right? And we showed that this is tight. All right, so I hope that this kind of answers why you should care about this goal. So with that assumption, let me proceed ahead and let me tell you about the previous implementation for partition oracles, right? What did they do? So the previous implementations were given by, as I said, Hasidim, Kellner, Newman and Onak, and Levy and Ron. And Hasidim and Kellner achieved an exponential in 1 over epsilon implementation. Think of D as a constant. Right? And Levy and Ron achieved a quasi-polynomial in 1 over epsilon query complexity implementation. All right, so now let me describe how these implementations go. So they follow one common underlying theme. So that common underlying theme is the following, that first what you do is that you describe a global algorithm that runs in full polynomial in n time and outputs for you a hyperfinite decomposition. And then you argue that, look, I'm going to faithfully simulate this global algorithm. Right? If you can like indeed do both of these steps, you have an honest to goodness implementation of partition oracle sitting in your hands. Okay. So now let's see more details of the implementation by Levy and Ron, because it's pretty much a refinement of the analysis by Hasidim et al. So let's see how they implemented a partition oracle. Right? So the idea is like something like the following, that I'm going to be proceeding in L rounds, where L is log of 1 over epsilon. Right? And I am going to produce a sequence of L graphs. The first graph that I start with, I call it G0. It's the source graph itself. And the way I'm going to produce Gi plus 1 from Gi is by identifying some random edges in Gi and contracting them all. All right. So think about one particular vertex V. What happens to this vertex V? So it's sitting inside some component in Z0. Then it got merged with like some of its neighbor. And you are now looking at this mega vertex. So notice that at any stage of this contraction-based procedure, the component that V belongs to remains connected. So even at the end of L steps, the mega node that V belongs to remains connected. And this mega node is what I'm going to return as the hyperfinite piece for the vertex V. All right. And you can track the size bounds, like all that straightforward stuff. The key idea is that, you know, in the ith iteration, what you will do is that you will pick some random edges, not uniformly random, right? I'll not go into details of how exactly these random edges are chosen. You choose some random edges and you contract all of them. And if any of the newly formed pieces happens to violate the size bound, you just undo that contraction. All right. So the size bound is kind of baked inside like this procedure. It will not produce crazily large pieces for you, right? So now let's see a quick sketch of the analysis that Levy and Ron used. So it roughly tells you the following, that what you're going to do is you will show that the number of edges that you cut in the graph Gi shrinks by at least a 0.99 factor as compared to the graph that you had in the previous step. This means that at the end of log 1 or epsilon rounds, the number of edges you are cutting is well within the size bound. It's big of epsilon dn. Okay? And the running time the authors show is the bound k, the piece size that you were looking for, to the number of rounds L that you performed. So that's quasi-polynomial. Number of rounds L is log 1 over epsilon. The piece size was 1 over epsilon square. So that explains the quasi-polynomial running time bound that I claimed earlier. Okay. So what I want to like say now is that naively speaking, at least the way this analysis, like at the caricature of this analysis in my head looks something like the following, that what Levy and Ron recommend we should do, this is a caricature. So apologies if this caricature is a huge oversimplification. It is. The idea is that like, you know, these pieces, they are found by performing a breadth-first search of depth L around some start vertices. Right? If that's what you believe, then you know your piece size is going to be polynomial in 1 epsilon. It's a bounded degree graph, max degree d. The piece size will not exceed some polynomial in 1 epsilon if it will be d to the L, right? So if you want to tighten the bolts on the analysis by Levy and Ron, and you want to produce a more efficient implementation of partition oracle that way, that's not going to work. Because if you really want a polynomial in 1 epsilon time implementation, you need to set this parameter L to be something little of log 1 over epsilon. Right? And that does not quite type check, because hyperfinite decompositions will necessarily produce pieces whose size grows as 1 epsilon square. Right? So there is little hope of making this approach work. If in fact the caricature I told you is not a terrible oversimplification. Right? Any questions so far? Okay, so let's continue. So now what I want to tell you is that it seems that some new ideas are needed to make progress on this question. And we had some progress on using random walks to do planarity testing. So we had some successes with implementing the one-sided testers and two-sided testers for planarity. So we decided that maybe that's the correct tool to rely on yet again. And towards this end, I'm going to now set up some notation. So I'm going to again look at the prototypical grid graph to get some inspiration from what a naive approach suggests over the grid. Right, and I'm going to, so I can very well pretend that my bounded degree graph is in fact deregular by adding self loops. All right, and I denote by PVL the distribution over endpoints that you get by performing an L-step random walk started at the vertex V. So PVL is just random walk matrix M to the LF power times the indicator for the vertex V. All right, and now let's think about what is this quantity, the 2 norm squared of PVL. All right, so if you consider performing an L-length walk from the source vertex V, the end vertex is square root L distance away from V in the horizontal direction and square root L distance away from vertex V in the vertical direction. So it's somehow trapped inside this root L by root L box around the start vertex. All right, and therefore one notes that the 2 norm squared of this distribution is fairly large. It's at least 1 over L. Okay, so we call such vertices non-leaky vertices because random walks or diffusions from the start vertex tend to get trapped in tiny little boxes around the start vertex. Okay, and going back to that theme that I told you earlier, that whatever you can show for a grid kind of holds for all bounded degree planar graphs. You can in fact show the following. So you have the following lemma that if you are given a bounded degree planar graph, then for an overwhelming majority of vertices, what you have is that the 2 norm squared of L-step random walks is fairly large. It's at least L to the negative 10. Right? So let's see how you'd prove this. So let's fix some hyperfinite decomposition with rate alpha. So you're deleting alpha and d edges, and your pieces, their size is 1 over alpha square. You should think of alpha as being epsilon square over L. And now I want to think about the following quantity, that imagine picking a random vertex, V, and imagine performing an L-length random walk out of this vertex. I'm interested in understanding that on an average, how many black cross edges does this walk encounter, right? So I'm interested in upper bounding this expectation. Oh, what? Okay, so that expectation did not appear. So that's nice. So is this pen visible? Okay, I hope I don't have to go through the entire stack. No. Okay. So I'm interested in the following expectation. Good. Good, right? Okay. So I pick some vertex V from the uniform distribution. Since my graph is deregular, the uniform distribution is also the stationary distribution of random walks. I'm interested in sampling an L-length walk from the start vertex, and I want to think about the number of cross edges that you see on this walk W. All right. So I'm doing one specific walk. The edge encountered at the ith step of this walk and the edge encountered at j step of this walk, they are highly correlated. But notice that since the walk starts at stationary distribution, at all subsequent steps it remains at stationary. Therefore, by a mere application of linearity, you notice that at every single step, the chance that you encounter a cut edge is proportional to a fraction of cut edges, alpha, which means that overall this quantity ends up being alpha times L. Right? So that's a pretty direct computation. Right? So you observe that that expectation is at most epsilon square over 100, which means the following, that, for at least 1 minus, oh, now those expectations appear. Okay, right. My apologies. So by Markov bound, what you can show is that for at least 1 minus epsilon fraction of start vertices, the probability that your walk W never leaves its home copy, never leaves the hyperfinite piece it originated in, is at least 1 minus epsilon, which tells you that, the 2 norm of PVL squared for an overwhelming majority of vertices is in fact large. It's at least some poly epsilon. All right. This is nice because this kind of suggests what global algorithm you can use once we have some right notation. So let me do that now. So I call such vertices non-leaky because the random walks from such vertices tends to get trapped in vicinity of that vertex, right? So they're not leaking. In an expander or a tree, these walks would just diffuse, right? Their 2 norm would crash rapidly. These 2 norms, they are kind of large, right? So I'm going to pretend that I have a deterministic procedure in my hand. I call this procedure C of S, where S is a start vertex. C of S is the vertex S itself if the vertex is leaky. Otherwise, C of S is refers to the following set. It's a set of all of those vertices that happen to be heavy hitters of the distribution PVL. All right? I just look at the heavy hitters of this distribution, and that's my set C of S. I'm going to pretend that this procedure is deterministic, and we have an implementation for it. It simplifies the discussion a lot. All right. So now I'm ready to show you my global algorithm. My global algorithm proceeds in the following manner. So, what I did is that I have this graph. I picked some start vertex, and I computed C of S around that vertex. Picked another vertex, computed C of S, C of S. I processed 3 different vertices, computed 3 different C of S's. I'm looking at a 4th vertex, and I want to process its C of S. I find it out. I'm happy. Now we look at the 5th vertex. C of S happens to overlap with some previously grayed out sets. All right. So what I do is that I say that, this is not the piece that I wanted to find. I only wanted to capture a fresh vertex that was not yet captured. So I update like C of S to include only the freshly captured vertices, that grayed out set over there. So that's the set that I'm going to return. And this is the set P of S that my global algorithm is going to output. So let's see the global algorithm. So first, let me emphasize what happened here. Okay, there was no blue stuff that was supposed to come, but my apologies. So the random tape, it's going to hold something. It holds a permutation of the vertex set. All right, that's what the random tape contains. Okay, in the ith iteration, what's going to happen is that there are a bunch of vertices that are not inside these gray boxes. I call them free vertices, capital F. All right, I pick the free vertex with the smallest index, and I find the set C of S. C of S, I think of it as the low conductance cut around S. So I find the low conductance cut around S. That's the set C of S. And I only consider the freshly captured vertices, and I throw them inside the set P of S. Right? The freshly captured set, the freshly captured vertices in F. Right? And I update the free set. That's my global algorithm. Right? So now what I want to describe is, okay. Right, so I want to describe my local algorithm, and the local algorithm will receive as input some vertex V, and I want to understand what I need to do in order to find the hyperfinite piece containing this vertex. So first things first, in order to find the hyperfinite piece containing the vertex V, it seems that I need to find a vertex S that led to the capture of V. Right? I need to find a vertex S that led to the capture of V. You with me so far? Okay. The other thing that I need to do is I need to find the free vertices inside the set C of S. Right? So these are the 2 challenges that I must handle. So it seems that, oh God, I'm sorry, everyone. Yeah. So I come to an important definition. So I define the anchor of the vertex V to be the vertex S if the global algorithm captured V while processing S. Right? So it's a property of the randomness of your initial random tape, which leads to S capturing V. Right? So anchor of V is said to be S if the global algorithm captures V while processing S. I hope these things do not show up again, but let's see. Right. So suppose you had a mysterious routine that could find for you the anchor of any given vertex. Right. Now I claim you can handle both the challenges. The first challenge is tautological. Right. The first challenge is tautological. Right. How do you address the second challenge? If you had a routine to find anchors, how do you address the second challenge? Does anybody want to make a guess? So you go over the set C of S and you ask each vertex, hey, who is your anchor? And all those vertices who report that their anchor is S, you collect them and that's your set P of S. All right. So let's keep going. Now, what I want to do is I want to implement the find anchor algorithm, and that's where my troubles begin. How do I find this anchor? Okay, so here is how I will go about this. I know that the vertex V is a heavy hitter of the distribution PVL. It's a deregular graph, right? Random walks are reversible. If random walks from S reach V after L steps with probability at least alpha, then random walks from V also reach S after L steps with probability at least alpha, right? So what I can do is that I can find a list of suspicious vertices where I reach with good probability. I start random walks from V. I collect all those vertices that I can reach with good probability. And I want to ask which one of them is my anchor. So I can look at the vertex with smallest index. I can check if this vertex is my anchor, right? And maybe that's all I need to do. I will find the vertex with smallest index, possibly U, that the vertex V can reach with good probability. I'll check if the C of U, if the set C of U contains the vertex V. But there is a problem. The problem is that, what if the vertex U was already captured? The vertex U could have already been captured and, dead men tell no tales, right? So that's the problem here, that I have a list of potential anchors and I'm worried that some of those anchors could already have been captured themselves, right? So this suggests that, there could be a recursive approach that one can use, that, when the algorithm was trying to capture V, at that instant of time, was a potential anchor already captured, right? And this recursive approach, we could not take it to its completion. We were not able to make this approach work. So we tried something different. What we tried instead was to change the global algorithm. And the change was to allow dead men to tell tales. So this is the modified global algorithm. So it says that, you start off by calling every single vertex free, and you just perform diffusions from every single vertex. You find the set C of S from your start vertex. You said that the freshly found piece is this C of S intersection F, right? And you just update the free set. That's the global algorithm you use. And this global algorithm has a corresponding local implementation that's easy enough. And now that thing should not have disappeared, but it disappeared, right? So, but there is still a danger. So I hope this part is clear, that this global algorithm is easy to implement locally. I have no idea what's happening anymore. I'm sorry. Right, I want to make sure that the new global algorithm appears. It's not appearing anymore. Sorry. Right, so this global algorithm where, I did diffusions from every single vertex, it's easy to implement locally. Because if you want to determine your anchor, what you will do is that you will identify a list of suspicious anchors, and the least index vertex in this suspect list, which captures me, is my anchor. So it's easy to implement locally. But we are not out of the woods yet. There is still some danger. And the danger is that, the set that I am guaranteed has small edge boundary to the outside world is the set C of S. The low conductance cut around S has a small edge boundary. I do not know any such bound about the set P of S, right? So the way we handle this is by proving an isoparametric statement. And this isoparametric statement tells you something of the following flavor. That suppose you have a large enough free set of size at least epsilon n. Then what you can show is that there are enough vertices left inside the free set. There are enough free vertices left such that diffusions from those free vertices capture many more free vertices. Right? Diffusions from if such free vertex S leads to the capture of many more. Right? Using this theorem, what you can show is that for every clustered vertex, the number of edges that you're cutting is at most epsilon d. And this allows you to conclude the epsilon and d bound. All right. So now, if you're interested in understanding whether there are more applications of this toolbox, Then Levy and Shoshan, immediately after our work went public, Levy and Shoshan gave a tester for Hamiltonicity on planar graphs. Right? And as I said, jointly with Sabya and Shesh, we gave an exponential and 1 epsilon square query tester for every single planar property, including the undecidable ones. Right? Now let me finish up with some open questions. So the first intriguing question is whether you can extend this notion to planar graphs of unbounded degree. These graphs are known to admit a decomposition called a Klein-Plotkin-Rao decomposition. And this decomposition, the subsets that you return, they no longer have small size, but they have small diameter. Right? So that's one interesting situation to think about. There could be other distributed applications for this task, because notice the key computation that enables everything is this computation. So if you have a decomposition that is series of decomposition that a graph admits, parameterized perhaps by some alpha, you have an entire list of decompositions that you could produce. So you get to define what a cluster means for you. And what I am hopeful of is that I can find clusters according to your definition. Hopefully in sublinear time, I can implement a partition oracle for the clustering definition you pick in sublinear time, assuming your definition of cluster has some nice behavior, right? And the final problem I have is that can you reduce the randomness? Can you get a bona fide LCA for hyperfinite decompositions? Right? So that's all I have. Thank you. Problems disappeared. The problems disappeared now. I have no idea why the problems disappeared. Sorry.
So what is missing now from obtaining LCA?
Uh,
If you wanted to turn your algorithm to LCA.
Right. I mean, so I've not thought that deeply about this, but it seems to me that it should be straightforward by hopefully some off-the-shelf application of Nissan-Wigderson style generators. But I've not Nissan-Wigderson style generators, but I have not looked at it carefully. So that's why I do not yet have a solution in my hand, and that's why I'm a bit reluctant to say that it's a closed problem. So yeah.
So you're currently using a long random sequence, and you want to say, can you somehow convert it into a short pseudo-random?
Absolutely. Absolutely.
Isn't that okay? The definition of LCA does not really require the randomness to be small. That's better.
Sorry, what?
Maybe I'm wrong, but by default, an LCA does not say your random tape should be small.
Oh, okay. Really, I did not know that.
Just you spend more time per query, but
Okay.
Wait,
Okay.
it's not required, but it's definitely, okay, so, but it's still a good open question, can you get it with a short random string? Because one possible application of LCAs is you could have many different copies of the LCAs computing in the wild, and they have some initial communication with the random string, but then they go off and do things independently, but they should be coordinated by this random string. So if it's short, that's big is better.
Okay. Any questions?
Okay. Well, let's thank